Hi everyone, it's Coach Fred, and today I'm doing exponential growth and decay. If you're in my class and you're working in your note packets, I do want you to complete the mixed review and go ahead and try those. And we're going to be talking about exponential functions and any function in the form of y equals ab to the x power, where a is greater than 0 and b is greater than 0 and b is not equal to 0 is called an exponential function with a base of b, okay? And so exponential functions can have something we call growth and something we call decay. So a growth function is when the b value is greater than 1. So we would call this exponential growth. And the graph is going to look like a curve. It's going to start off pretty slow, and then all of a sudden, it's going to grow pretty quickly. Similar to what happened with COVID, right? A couple cases, then lots more cases, then lots more cases, and then eventually it just skyrocketed. Exponential decay is when the b value is actually between 0 and 1, so the b value is a fraction. All right, so when that's happening, we're going to call that decay. And often we talk about decay of maybe like a population, and it's going to decay like that. But the interesting thing about an exponential growth and decay function is that because it's exponential, like I give you, I don't know, y equals 2 to the x. That's an exponential growth equation. There's no value for x that I can put in that is going to actually make it reach 0. Meaning, like if I put in, I don't know, 2 to the negative 100, that's just going to give me 1 all over 2 to the 100, a really, really small number. So regardless of how negative the number is, the number itself will never reach 0. Also will never reach a negative value. So what that means is that there's an asymptote in this graph. Remember, we've worked with asymptotes so far this year. So there's an asymptote at the line y equals 0 for both exponential growth and decay. So unless the graph is shifted up or down, that asymptote is going to be there. So there's a couple key things that we're going to want to know about the graph. We're going to need to know the general shape, how to tell if it's growth or decay. So we always look at the b value. You are going to always want the y-intercept. So I'm going to use this y equals 2 to the x, or y equals, how about I do 2 times 3 to the x as an example. So the cool thing here is that if I let x be 0, we do have to remember that rule for exponents from our last unit, that anything raised to the 0 power is the number 1. So if we think about that, that would make this y equals 2 times 1, so y equals 2. So my y-intercept is always going to be that value, the a value, if the graph isn't shifted, so just the basic graph. So 0, comma a would be the y-intercept. To find an additional point, we just plug in x values, right? We can find any additional point. So like in this graph, if I plugged in 1, I would get 3 to the 1, which is 3 times 2, which is 6. So I would get like 1, 6, right? Or I could put in 2. I could put in negative 1. Let's talk about that one for a second. If I put in negative 1, that's 3 to the negative 1, which would be 2 times 1/3. So it would be 2/3. So the thing that's telling me is that there really is no value that I'm restricted from putting into the function, which means the domain is going to be all real numbers, negative infinity to infinity. We already talked about the equation of the asymptote, so like y equals 0. And the range is always going to either be above the asymptote, could be below it if I reflect the graph. So in this case, it would be 0 to infinity, okay? Now, these exponential functions we're going to be working with a lot, and their inverse function, which we call the logarithmic function. All right, so let's look at some graphs. Here's what I'd want you to be able to do on any graph. Number 1, I'd want you to be able to tell me if it's growth or decay. So always look at the form y equals ab to the x. So this is telling me it's growth. The y-intercept would be in this case where x is 0, so 0, comma 3. You should be able to get me an additional point, so 1, comma 6. My domain, again, no restricted values, so negative infinity to infinity. And then our equation of our asymptote is y equals 0. So once I have that, I can do my range, so 0 to infinity. All right. Now, I want us to think about how we graph it, but I also want us to think about the table. So I'm going to actually make my X and my Y grid. So I have 0, 3, and then 1, 1, 2, 3, 4, 5, 6. I've got this horizontal asymptote I'm going to put in. But if I wanted to make more points, I certainly could. Let's see what happens when I do that. All right, so I put in -1. That gives me 3 times 2 to the -1. So 3 times 1/2, so 3 halves. So -1 would be at 1.5. I put in 0, we know we already get 3. I put in 1, I get 6. I put in 2. That gives me 3 times 2 to the 2 power. 2 to the 2 is 4. 4 times 3 is 12. So no matter what, the graph is still going to take on this shape of an exponential function. Now, the thing that's really interesting about an exponential function that's different than linear is that if you look at this, the change behavior in the y's is that each time I'm being multiplied by a number, or that the ratio from term to term is constant. The ratio is constant. So I want you to think about how that differs from a linear function. Linears are constant rate of changes, meaning if I had a table and it was 1, 2, 3, and then 5, 7, 9, you're adding 2 every time. Whereas exponential, we really want to think about 1, 2, 3, 5, 15, 45. You can see that 5 times 3 is going to give me 15, and 5 times 3 gives me 45, or the ratio of 15 over 5 is equal to 45 over 15, which again shows us 3. And where does that 3 play a role in the graph? Well, in this case, it would be the b value. So like our graph here, it was 2. So that tells me my growth factor. Okay? All right, so what about decay? Decay is going to look very similar. I've got 3 times 1/2 to the x. So my growth, this would be decay because b is less than 1 but greater than 0. My y-intercept isn't going to change. So 0, 3. My additional point, though, so like you can plug in any point, right? Because our domain is -infinity to infinity. But you're really going to want to think about what the best points to plug in would be. So like I'm thinking about this. If I put in -1, think about that. Remember, if we have a fraction raised to a negative exponent, we flip it and make the exponent positive. So that would lead me to that. So if I plugged in -1, I'm going to get 6. Because if I plug in 1, which I could, I'm going to get 1/2 to the 1, which is 3 halves. So I get a fraction, so not so pretty. All right, so again, I'm going to put in that -1, 6, but it really doesn't matter as long as you know the general shape to the graph. So here we go. Make my XY coordinate plane, and I plug in 0, 3, 1, 2, 3, -1, 6. I'll put in that 1, 1/2. Oops, I did that wrong. -1, 6. And then 1, 1.5 is going to be right about there. And so you can see, instead of the graph growing from left to right, it is falling from left to right, and that's why we call it decay. Keep in mind, we always read those graphs from left to right. That equation of the asymptote still is going to be 0 because this graph is never going to be able to reach 0 no matter what input I put in. And therefore, my range would be 0 is greater, or 0 to infinity. We're going to talk about other ways that we could actually write this function if we wanted to, using the laws of exponents in another unit. Okay? All right, guys, hopefully that was a helpful introduction to exponential functions. You're going to move on to video 2. I hope you all have a great night.